Thank you for the introduction, and also thank you for the opportunity to give this talk here. It's really a great pleasure. I'm Peter. I'm a PhD student in the group of Harald Weinfurter from the LMU Munich, and I'm going to present you the results, the experimental results from our handheld QKD experiment. There exists a lot of applications for a small distance QKD. Yesterday we already heard a talk about this. For example, the transaction at an ATM or a point of sale or access to a quantum network. But in order to achieve this, we have to shrink the size of the QKD setups. And at least for one part of it. And this was mainly one goal from this project, and the second goal was to build a receiver, a tracking receiver, where we then can really show a handheld scenario where the user is holding the device in the hand. And this is our approach. For the sender device, we wanted to keep it as simple as possible, and therefore we choose the polarization encoded BB84 protocol, and as a laser source we have 4 VCSELs, which are in array form where you can buy it, with a pitch of 250 microns, then followed by a microlens array in order to focus the light coming from the diodes, then a polarizer array, homemade, in order to set the polarization states, and then to recombine the 4 paths of the diodes, we choose a waveguide circuit where 3 50-50 beam splitters are embedded, and finally we have a bright visible beacon laser for aiming and for the tracking and also for the synchronization of the clocks. We drive the diodes with a repetition rate of 100 megahertz, and we achieve a pulse duration of 200 picoseconds. Tests from us showed that we can also push this further and reach shorter pulse durations. We can show that the temporal overlap of the 4 diodes is almost perfect, and one interesting thing about the diodes is that the degree of polarization is quite low in pulsed mode, which allows us then to reset the polarization, and we make this by a wire grid polarizer array, which is basically a 265 nanometer thick gold foil, and we create such patterns on this gold foil by using a focused ion beam. And you can see here these gratings made by the beam, and we reach extinction ratios well above 1 to 1000. And the waveguide circuit is produced by the group of Roberto Salmone in Milan. They use a femtosecond laser writing. The birefringence is 7 times 10 to the power of -5, and the path attenuation is 0.5 dB per centimeter. And there's also a 3D, or the waveguides are structured such that they create a sort of a 3D structure in order to get an optimal coupling of V and H. So, and this is basically the result. It's a prototype. It's a little bit oversized, at least the aluminum box. But in the front part of the aluminum box, we have the sending optics. Here, zoom in. The biggest part, or mostly dominated by the waveguide circuit, and also the connector and the PCB, but it's still quite small. Then the connection to the electronics, with an FPGA, and maybe you can see also the 4 driver lines here in order to drive the diodes. We also characterized our module in terms of the polarization states. Therefore, we made a full tomography and calculated the Stokes components well, and that's the result. These states are quite or slightly rotated and also have elliptical components. This is mainly caused by the birefringence of the waveguide and also from the dichroid beam splitter. And however, we can compensate for that and end up with a very nice QBER of around 1.5% initial QBER. Then we also want to implement or to calculate a quality factor which simply says something about how complementary the bases are really. I mean, if we choose really perfect BB84 states, this value would be 1, and if the states are not really perfect, we get this value here. And despite our states are not so bad, at least for the compensated one, this is a very steep behavior at the logarithm. Here we end up with a value of 0.75. How does our receiver works? Well, we have here our LS module. The beam goes this way and then this way. Here the beacon beam is coupled out, and the signal beam is analyzed by the polarization analysis unit. We have a passive 50-50 choice, and then 4 APDs for the 4 polarization states. We need a good tracking, beam tracking. This is done by a movable voice coil mirror, feedback from a quadrant photodiode, and the capture angle of this is ±3 degrees, and there would be a very dangerous side channel, this spatial mode side channel, which means if we would allow, or if we allow Eve to change the incoming angle, she is more or less free to choose which one of the detectors should click. And we close this side channel simply by restricting the acceptance angle to 0.08 degree. And you can imagine if you stand in front of a receiver with such a small acceptance angle, you will never couple in something, and therefore we have to, we need an efficient tracking system, and we reach values about, in average, about 20%, up to 1/3 compared to the stationary case. So then we have, there's another degree of freedom. There's the user can rotate the hand, and we compensate these rotations by moving a motorized half-wave plate, and the feedback is given by a mobile phone placed on top of the sender. And just because this is the most impressive thing for the guys which are visiting us, that we really can establish such a link between a mobile phone and a computer, and then a fast photodiode for synchronization, and one compensation step in order to compensate for the rotations, the initial rotations by Alice, and also the rotations along the path in Bob. So now we can make QKD, and well, what you see here is the raw and sifted Q rate, as well as the QBER. The QBER is quite low, below 2%, and we end up with a secure key rate about 148 kilobits. And what you can see here is basically that the module is really stable, and that we can use that. Now we can make handheld QKD. And what you can see here is basically a typical run that we made. In the beginning, there we placed the sending module in front of the receiver, not very carefully. You see that it would be possible to reach, if we really align this carefully, we would reach higher key rates or higher detection rates. And we put this, or we take the sender, have a sort of a aiming phase here, and start then to get some signals from the sender. And now, as you all know, the function for the rates, I mean, there's the Cuber, there's the mean photon number, and there's also a value for the transmission. And what value should we use? Well, here we defined a threshold in order not to overestimate our system, and signals above the threshold are discarded. They are used for the secret key, and below the threshold they are discarded. And what's also important is that signals which are above the threshold are also evaluated by the transmission value for the threshold. And so we never overestimate our system. So, and what you can see here is basically a table of results. I showed you the last one simply because it represents bestly the average values. I can also show you the best and the worst one. There's, on the first glance, there's not a big difference, of course. The link efficiency, you have some times where the link efficiency is quite well, and if the user is quite nervous and or something else, the link efficiency is not as good, but well, it really depends in the end on the user. And in average, we get a handheld efficiency of around 20%, in maximum 30%, a Cuber of 2.4%, and an average secret key rate, including this quality factor of 6.2 kilobits per second. And I want to say that this table is made by 4 untrained users. Yeah? All of them made 2 runs, and they always achieve a secret key in the end. So to conclude, I showed you a small QKD transmitter and a tracking receiver. We achieved a handheld operation where we got secure key rates about in the kilobits regime. We wanted, of course, we want to implement decoy state protocol. Then we can achieve much higher key rates. We generate sub-nanosecond pulses, which means that we could increase the clock rate. Unfortunately, the spectrum of our 4 diodes does not overlap. We have to find a solution for that, this is a side channel which we have to close. And for future projects, we want to merge our system with commercial products or AES encryptor, and we want to put our optics onto a CubeSat and try to exchange a key from the orbit. So thank you for your attention.